Alrighty, hello everybody. So now we're continuing our adventures into other sequential data structures, and we're going to talk about queues. So they're closely related to stacks, but they kind of work in a little bit of a different way here. You're going to hear me say the phrase like a stack, like a lot in this video, so get used to it there. So like a stack, a queue has operations where we can add new elements, we can remove elements, and of course we can check to see if the queue is empty, and we need the ability to check and see if it's empty because removing the element is illegal if there isn't anything to remove. The main difference is that in a stack, right, we added things on the top and we removed them from the top. So like they're added and removed on the same end of the sequence there, like that. Whereas in a queue, we add things to one end and then remove them from the other end, from the opposite side there. It doesn't matter what you call the ends, right? Whether you call them like the top and the bottom or the front and the back or whatever like that right there, right? If you're adding and removing things on the same end, you have a stack. If you're adding and removing things on opposite ends, you have a queue there. So usually we'll sort of visualize a queue by drawing it like horizontally with the back on the left. So this is where things come in, and then the front on the right there, like that, as opposed to a stack, which we visualize vertically, like a stack of whatever's there, like that. So like stacks, queues have sort of three core operations and then three extra operations. So our core operations to add new items, that's called an enqueue. So we enqueue an item, that adds it to the back of the queue, there like that. To remove an item, just like with a stack, we don't say which item to remove, we dequeue, and that removes whatever is at the front of the queue there, like that. And then we can ask if the queue is empty because it's illegal to try and dequeue if the queue is empty there. For our other operations, just like with a stack, we have a way to sort of peek at what will be the next thing to be removed, the next thing to be dequeued. This is sometimes called front, but like down here, it's sometimes called peek, or in the like the C++ standard library, if you hashtag include queue, like that, right? The standard library queue class calls this operation top, which is weird because a queue doesn't have a top. It has a front and a back there, but that's just what it's called there. But whatever you call it, right, it's a way to sort of look at what will be the next thing to be removed without actually removing it yet there. If we build a queue on an array, then it could possibly become full. So we have a way to check to see if it's full. It's illegal to enqueue if the queue is full, just like it is illegal to dequeue if the queue is empty. And then it can be convenient to have a way of asking, like, what's the size of the queue? What's the number of things that are currently in the queue there, like that? Basically, how many dequeues could I do before the queue became empty there, like that? So those are our sort of operations that we have there. So let's just trace through a few queue operations here and see how the queue sort of evolves and how things will look different from a stack there, like that. So initially, our queue starts out as empty, right? We don't have anything in it. So we enqueue 1, and it goes in the queue. So it entered on the back of the queue there, like that. Then we enqueue 2. So 2 comes in at the back, which kind of like, has the effect of sort of visually pushing like 1 forward there, like that. And then we enqueue 3. So now the contents of our queue looks like this. So 3 is the most recently added item. It's at the back of the queue. And then 1 is the oldest item. It is at the front of the queue there. And of course, empty is false now because the queue's not empty. So when we start dequeuing, the first thing to come out is going to be the 1. So the oldest item in the queue is the first one to come out there. Then we're going to get out 2. And then we get out 3 here. So notice like the difference between this and the stack here. In the stack, these came out in the reverse of the order that we put them in. They came out as 3, 2, 1. Here they come out in the same order that we put them in there, like that. So queues sort of preserve the order of things as they're added there. And that might seem like, a subtle, like, just a small change there, but it has like a big effect on like when we actually go to use a queue or a stack there, like the order in which things sort of happen there. So both stacks and queues, like they have a similar like interface, right? Even though we give them different names, there's like an operation to add things, an operation to remove things, and an operation to check and see if it's empty. So you could switch them out like relatively easily. If you had like an algorithm that used a stack, you could change it to use a queue without, you know, sort of too much work there. But switching them around, right? The difference in like how things come out when we remove them there has a sort of dramatic effect on the algorithm that we're sort of doing. So I mentioned in the stack video that stacks are sometimes called LIFOs, last in, first out. So the most recently added element is the first next element to be removed, right? Like the sort of most recent thing to go in is the next thing that's going to come out here. Whereas queues are sometimes called FIFOs, first in, first out. So the oldest element, the first element that we added, like the number 1, right, is the first element to be removed there. The first thing we put in, 1, is the first thing to be dequeued like that. You can think of it as like stacks are sort of like prioritizing like new things that we put into there. So as soon as we push something onto a stack, it becomes the top and we sort of jump on that there. Like it's like, oh, this is the new most important thing that I'm supposed to like work on here. Whereas queues are more about like keeping things fair, right? New tasks go to the back of the line, so they have to wait for everybody that's in front of them to sort of finish before they sort of get their turn there like that. So queues aren't more of like, oh, something new, I better jump on it. They're more like, okay, you can wait until I've finished all the other stuff that I'm sort of currently doing there. Like stacks, again, like there's 2 error conditions that can occur with queues, and they're sort of like the queue, you know, analogs to the stack errors. So a queue underflow occurs if you try to dequeue or otherwise access the front while the queue is empty. An empty queue doesn't have a front, so you can't access it. And if you have an array-based queue that can become full, then trying to enqueue into it is a queue overflow, right? I can't add new items to a queue that is already sort of full there like that. And you know, like before, how you deal with these errors depends on what your sort of, you know, usage is. So maybe these are exceptions that you throw or messages that you print, or in the case of like a queue overflow, maybe we don't do anything, right? Like maybe if you try to enqueue into a full queue, the thing you were trying to add just gets like dropped or something like that. So you sort of choose, you know, how these are handled here, but you have to be aware that like, okay, these things could happen. What should happen in these cases? We can build a queue just like a stack on top of a linked list or on top of an array or a vector like that. Same as before, we want all of our core operations and hopefully all the extra ones to run in constant time there. If we build a queue on top of an array, we can have a sort of fixed maximum capacity, or we can use like the vector trick to make it like grow, where we allocate a new array of double capacity and sort of copy everything over. That would make enqueue run in O1 amortized time, but that's still okay, right? As long as we're sort of using it enough, it'll average out to O1 there like that. So let's look at like a queue based on a linked list here. So like for a stack here, we basically have to decide which ends of the list are we going to use here. So enqueue and dequeue always operate on opposite ends here. So that means like if we choose to make enqueue add new things at the head, then dequeue is forced to remove them from the tail there. If I enqueue at the head and I dequeue at the head, I don't have a queue. I have a stack. So they have to operate on opposite ends here. So it's either add at the head, remove at the tail, or add at the tail, remove at the head. And just like with a stack, we'll see that we'll have a strong preference for one of these 2 choices based on the runtime complexity of the operations involved here. But let's go through them and look, right? So if we enqueue at the head and then we dequeue at the tail, that means enqueue basically is doing a push front, and push front is a constant time operation. So that's okay. We're good there, right? But then that forces dequeue to use pop back, right? It has to operate on the opposite end. So this is front, that means this one has to be back. And pop back on a singly linked list is O of n, right? It runs in linear time there. And that's not good. Now we could make this O of 1 by making our list like a doubly linked list, but then we're paying for like, an extra pointer in every single node just to make this one operation take constant time there. We do need both head and tail pointers, right? Because we're adding stuff to the back and we're, we're adding stuff to the front and we're removing stuff from the back. So we need both our head and our tail pointers there. But DQ, the sort of big failing for this one, right, is DQ will be O of N for singly linked list here. So that kind of rules out this one unless we have some particular reason why we want to do it this way. Now, if we look at the other alternative, we're going to add stuff at the tail and remove it at the head here. So that means our NQ is going to map to pushback. And pushback runs in constant time, but that means we need to have a tail pointer. So we're sort of, we're required to have a tail pointer, but that's just one extra pointer in our class. It's not like a doubly linked list where it's like an extra pointer in every single node. Then that means that DQ is going to be a pop front, which is also constant time. So those are both constant time. That's good there. Technically, we only need a head pointer, but if we want to be able to do this pushback in constant time, we will need a tail pointer there like that. So like, you could get away with only having a head pointer, but that would make the NQ run in O of N time, and we're trying to avoid that. So like we won't sort of like take advantage of the fact that we could get away without a tail pointer there like that. So the important thing about this one, right, is both NQ and DQ run in constant time. So we've got that, that's what we want. So this one here is the pattern that we're going to use. Add new things at the tail, remove them from the head. You can remember this because like, a queue is sort of like a fancy word for like a line of people, like, at the Disneyland or the post office or whatever. So you get into line at the back of the line, the tail there. And you exit the line when you get to the front of the line. That's where you get to go on the ride or whatever. So like you get pushed back and then pop fronted there like that. So we're basically implementing pushback and pop front. Now for the linked list, we wrote those in terms of insert here. But here we can sort of like simplify things because we don't need to worry about all the different cases, right? So we're doing a pushback for NQ and a pop front for DQ. So for pushback, that's an insert after the tail. We have case 2, which is where we insert after the tail. And then we have case 3, which is when the list is empty. And that's a special case because we need to update both the head and the tail in that case. So those are the only two cases we need to worry about for insert. And then for erase, we're erasing the head, right? So case number 1 is where we're erasing the head, but the list is not going to be empty after we're done. So the list will still have something in it. We have at least 2 nodes. And then case 3 is where we're erasing the head, but the head is also the tail. The list is going to be empty after we're done. And this is a special case because we have to update the tail pointer in it here. So case 3 for both of these is the special case where we need to update both the head and the tail. In the stack, we didn't have a tail pointer, so we didn't have a special case for case 3. Here we do, so we'll need to sort of have that as a special case there. This should look familiar, right? This is basically under the hood our linked list class. We have the same node structure as before. We have our head and our tail pointers, but then publicly we don't have any of the linked list operations. We have the queue operations. We have the core operations, and then the 3 sort of extra optional operations. We have a size member in our class, and that is just to make the size function run in constant time. If I didn't need the size function, if that wasn't like a function that we were required to do, then I wouldn't need the int sz data member there like that. Like that's only there to make the size run in constant time. The first 4 here, empty, full, front, and size, those are all easy, and they're all going to run in constant time here. So when is the queue empty? The queue is empty when the list is empty. When is the list empty? It is empty when the head is null pointer. We could also check the size there as well. That would also work. When is the queue full? Well, it's based on a linked list, so it's never full, right? Like we can always create more nodes until we run completely out of memory, but then that's like somebody else's problem. That's not our sort of issue there. So we just return false, like no, we're never full. If you want to get the front of the queue, we do have to check and make sure that there is actually a front there. Make sure that we're not empty, so we do that first. But otherwise, the head is the front, so we just return the value inside of the head there. So that's how we do front, right? And then the whole reason why we added that sz variable to our class was so that the size function could just return it. We don't have to like do a loop to count nodes or anything like that. We're just like, what's the size? It's sz. That's just what it is. All right, so let's look at enqueue in the linked list based implementation. So we have two cases, case 2 and case 3 to worry about here. And the code will be pretty similar, only one of the steps will be different here. So for case 2 here, first thing we're going to create the new node. So I've already done that. That's like n right there. Then we're going to set n's next to null pointer because we're inserting after the tail. So n is going to become the new tail here. So n's next is a null pointer. The tail's next is always a null pointer. Then we set the old tails next. So this is the old tails next right there, right? To point to n. And then finally we update the tail to point to n there like that. So just 4 steps like that. For case 3, we can use the same steps except for one of them. One of them is going to change here. So step 1 is the same, right? Create a new node n. Step 2 is also the same, set n's next to null pointer. Step 3, so up here, step 3 is set the tails next to n. Because we have a tail, we have a node there like that, right? Down here though, our tail is null pointer. So in place of that, we're going to set the head to point to n. That's the only difference here is step number 3. And then step 4 is set the tail to point to n here. So all 4 of the steps are the same except for step number 3. So instead of writing this as like a big, okay, if do this, else do this, we can just do step number 1, do step number 2, wrap step 3 in an if else, and then do step number 4. So that's what this looks over here. This is step 1 right here. Step 1 is the same across both cases. This is step 2 over there. This here is both versions of step 3 wrapped up in an if else that basically says like which one do you want, and then this is step number 4 down there. Now, like with the stack one, you can kind of make a simplified version of this, but I'm not sure if it's actually like simpler. So this one over here does the same thing as the version on the left, but it does it more compactly. I'm not sure if it's actually like really simpler here, but it does the same thing there. So I'll let you be the judge of which one you sort of like better. Of course, in both of them, we have to increment the size so that size is always consistent with the number of nodes in the list there. Now, again, for dequeue, we're basically doing an erase, but we only care about case 1 and case 3. We're not erasing from like the middle or the end. We're only erasing the head here. So in case number 1, we're going to set n to point to the head. And we're doing that because we're going to move the head pointer over here, and I need to have a pointer to this node so that I can delete it when I'm sort of done with the whole process there. Like literally the next step is set the head to point to the heads next there like that. So at this point, the only pointer pointing to the old head is n. So I'm not going to do anything in step 3. I'm leaving that blank because we're going to use it down here in case number 3 there. So I'm just sort of like, hey, nothing happens in step number 3. But then in step number 4, we can delete n at that point there. So just like with the enqueue, the only difference between case 1 and case 3 is going to be step number 3. Up here we do nothing. Down here we're going to do something in step number 3. So step 1 is exactly the same. We set n to point to the head. So case 3 is where there's only one node left. So that node is both the tail and the head here. So n points to the head. You could also point it to the tail, right? But if we set it to point to the head, then that is the same as step number 1 from up there. Then we're going to set the head to point to null pointer. The list is going to be empty when we're done here, so the head had better be null pointer. But we could get that null pointer from the heads next, so we could use the same code as we used in case 1. Step 3 is set the tail to null pointer. So if the list is empty, both the head and the tail should be null pointer. And then step number 4 is to delete n. So again, the only step where we do anything different is step number 3. So just like for enqueue, we can write, the code for step 1, the code for step 2, and then just wrap step 3 in like an if to sort of say like, do we need to do this or not there like that. So that looks like this. Now for dequeue, we do need to check for queue underflow before we start, right? We can't dequeue from an empty list, so we do that up front. This here is step number 1. This is step number 2. This in here inside of the if is step 3 if we need to do it. We don't always need to do it. And then this down here is step number 4. This other stuff around here, right, is just because we want to return the value that we are dequeuing. So we have to save that value before we delete the node, because you can't access the value, after you've deleted the node there like that. And of course, we have to remember to decrement SZ because we want it to be in sync with the number of nodes there like that. You could probably compress this down and like make it shorter, but it's not really like simpler at all there like that. It's because we have to capture the value before we delete it and stuff like that. So this is sort of the canonical version of dequeue there like that. Now, when it comes to queues on top of arrays, there's a few things that aren't completely obvious here, but we'll start with the sort of stuff that we definitely need, right? So privately, we have a pointer to the array that backs the queue. We need to know how big that array is so that we can know when we're full. So that's our capacity. And then we'll figure out as we go along, like what else we need here, right? But we've got our core operations over here, and then also our optional operations down here, like that. So we'll flesh out this part here to see what else we need here. So let's just start with like an empty queue, right? And we'll just follow the example from the beginning. So we're going to enqueue 1, 2, 3, and then dequeue 3 elements here. And we'll just sort of see where should they go in the array here. So we're starting with a capacity of 8. So we're going to enqueue 1, and then where do we want to put 1 in the array? We can put it anywhere, right? The whole array belongs to us here. But we want to follow some kind of pattern that will be sort of easy to see, okay, here's the part of the array that we're using, and here's the part that is still available for later use here. So let's just put it at array index 0. So we'll put the 1 right there like that. So then next we're going to enqueue 2, right? So same deal, where should we put the 2? We can put it anywhere, but for consistency, let's just say we're going to put it at array index 1. So then the 2 goes there. And then we enqueue 3, right? So for consistency, we're going to put 3 there. So over here, this is the front of the queue, right? And then over here, this is the back of the queue, like that. So in terms of the array, the front of the queue is at index 0, and then the back of the queue is at index 3. Or if you want to, you could consider the back of the queue to be here, the sort of next available spot in the array there, like that. Okay, so we at least need to keep track of where the back is, so that we know when we enqueue something, where it needs to go there, like that. So for us, we're gonna keep the back of variable b as the next available spot. So it is basically 1 after the last element that we just enqueued there, like that. So to enqueue a new item, you just put the new item here, and then you increment b to move b onto the next available spot there, like that. So we have to add int b to the back of our queue here. Now let's do some dequeues, right? So we're going to dequeue, and that's going to remove the number 1 here. So that should remove that. Now, just like with a stack, we don't actually remove it from the array, right? The 1 is still going to be there. We just need to keep track of the fact that that spot in the array is available for use there. So then we're going to dequeue the next item, right? So next we're going to dequeue 2. So that means we want to get rid of the 2 from the array there. So again, we're not actually going to delete it out of the array. It's still there. We just need some way of keeping track of oh, that spot's now available as well there. And then the last dequeue sort of dequeues 3 like that. So the same way that we did with the back, right, we're going to have an index that keeps track of where the front of the queue is. So when the queue has 3 elements in it here, the queue has sort of all 3 things in it, this is what it will look like here. The back of the queue tells me where the next available spot is. So that tells me where the next NQ is going to go. And then the front is at index 0, telling me where is the front of the queue there. So we have to add these two things to our queue class to keep track of that information. And if you rewind it sort of like back to the beginning, right, this is the initial state. This is what an empty queue looks like, is B and F are both at index 0 there, like that. So there's nothing in the queue in this case here, like that. Okay, so then we can see that our NQ and our DQ should work something like this. So to NQ something, you place it in the array at the back of the queue at index B, and then you increment B. And then to DQ, we capture the element at the front of the queue, we increment the front, and then we return whatever sort of X is there, like that, right? Note that like in a stack, right, we had one variable that we incremented and decremented. Here we have two variables and we increment both of them, right? There's no decrementing happening here. It's all increments. Now, if you're thinking ahead a little bit here, you might be like, wait a minute, this is something's going to go wrong at some point here. So let's just keep NQing and DQing for a little bit and sort of see how things play out, right? So we'll NQ 1, and then 2, and then 3. So this is where we're sort of at before, right? Then we do a DQ. We DQ 1, that moves F up, right? We DQ 2, that moves F up like that. Then let's NQ a few more things. So we'll NQ 4, we'll NQ 5, we'll NQ 6. And then maybe we'll do a DQ, so we DQ 3, then we'll NQ 7, and then we'll NQ 8. So at this point, the contents of my queue, the front of my queue is 4, and the last element is 8. So my queue, if I were to draw it out, looks like this, right? It's 4 at the front, 5, 6, 7, and then 8 at the back there. Like this is the front, and then this is the back. But I can't put the back out here at index 8 because that's beyond the end of the array there, right? So like the back can't be that. So like we have to do something with B after this NQ right here. Because here's the thing, right? When B is out here at index 8, it kind of looks like the queue is full. It looks like we have all the sort of items that we can have here because, you know, B can't go any further. We can't add any new things. But the queue is clearly not full. We only have 5 things in our queue, and we have a capacity of 8. Like we have these 3 spots over here that are empty. How do we make use of them? Like we should be able to do another NQ, but like if we NQ 9, like where's it going to go? Like it can't go here. That's beyond the end of the array there, like that. So how are we going to make use of all the space that we have in the array? So the trick is pretty simple. When we need to go beyond the end of the array, we just wrap it back around to the beginning, right? The available space is back at 0. So if we increment B or F, and that goes beyond the end of the array, we just reset it back to index 0. So this is called a circular buffer here. We're basically pretending that if you go off the end of the array, you just sort of wrap back around to the beginning here. So if we sort of go back here, right, we do that final NQ, 8 goes here. After that NQ, B would cycle back around over to here, so that when we do the final NQ of 9, right, that places 9 there, and then B moves up to the next position here at index 1. This is the next available spot at index 1, the next place that I could sort of put something in there. So that lets me take sort of full advantage of all the space that I have in my queue array there, like that. So our final implementation looks like this, right? Like this part stays the same, but we added this new bit here, which is if we've gone past the end of the array, wrap back around to 0 there, like that. Same thing, like this part stays the same, incrementing F, but then we check to see if F goes beyond the end, and if it does, we wrap it back around to 0. The only problem is, like, now how do we find the size, the length of the queue here? Because the sort of normal way things look is we have F less than or equal to B there. But B could go off the end and then wrap around so that we actually have B less than F there. And the size will be different depending on sort of which arrangement we're in here. So if we're in f less than or equal to b, then we just subtract. B minus f gives us the length of the queue there like that. But if we're sort of inverted, right, if b is less than f here, then that means we're in, let me go back here for a second, right? We're in this kind of a shape here, where part of the queue is over here on the right-hand part of the array, and then part of the queue is over here on the left-hand part of the array. So the total length is the sum of those two parts here. So the length of the queue is cap minus f plus b. The cap minus f part, that's how much stuff is on the right-hand side there. And then the b part is how much stuff is on the left-hand side here. So 0 is here, b is there, f is there, and then cap is out here. So cap minus f gives me how much stuff is over here. And then you can think of this as like b minus 0, but that's just b, right? Tells me how much stuff is there. The sum of those two things is the amount of stuff that we have in total. So our size function just checks to see which of those two cases are we in, and then returns the appropriate value depending on which one we're in there like that. And then all the other functions can be based off of size, right? So when are we empty? When the size is 0. When are we full? When the size is equal to cap here. The front is just as long as we're not empty, whatever is at the index of f in the array there like that. So queues don't have as many kind of obvious applications as stacks here like that. That's partly because they're sort of more limited in terms of like how new and old things can communicate with each other. So like in a stack, right, if we're working on something like a task, right, and we discover that we need to do a subtask, the subtask and the old task are sort of like neighbors in the stack, right? Like a new task gets pushed just on top of the sort of previous old task there. So it's easy to send information back and forth between them. But in a queue, new elements go way at the back end of the queue. And a new sort of like thing is going to go at the back of the queue. The thing that spawned it at the front of the queue is going to be gone. It's going to be like, dequeued after a long time there. So there's not as many sort of like communication opportunities. Queues are mostly used for like independent tasks here, where the tasks aren't so much like communicating with each other. They're just doing their thing, and we're just using a queue to keep track of like, keep things sort of fair, keep things in line there like that. But there are some algorithms where you can literally just swap out a queue for a stack and get like the same algorithm, but with a sort of slightly different like pattern to how it works there like that. Yeah, so like queues used to keep things like fair. A lot of times, like what we'll do is after we dequeue something, we'll add it back into the queue. We'll put it back in the back of the line here. So if we have a queue that is sort of tracking some tasks here, as long as there are still some tasks in the queue, we'll pull a task out, we'll sort of process it, and maybe processing it causes it to be finished. But if it's not finished, we put it back at the back of the line there. So that keeps the sort of everything fair, right? Like no task gets more time than any other task, because when you're sort of like after you get your turn, you have to go back to the back of the line if you want to go around again there like that. So that's queues, right? Like there's sort of queues and stacks are kind of like mathematical neighbors in a sense. They're in the way that they work. And they're both sort of things that we can build on top of linked lists and stacks there like that, right? So next week we'll have a review for our first midterm, and then that'll sort of like, then we'll have the actual sort of midterm as like a Canvas quiz with some questions there. But we'll talk more about that in the actual midterm review. That's it for now, everybody.